What I would like to talk about today is about my research, which is not so diverse in the end. It's all about computing. It's just that computing has applications in many different fields. And I would like to discuss three elements that you will see repeatedly today. One is about laws, not necessarily the law of the land, but physical laws. It's going to have to do with data, and there's going to be about humans. The dots that you see here is what we have been doing over the centuries in science, connecting or deriving physical laws by human intuition, by observation, by interaction with data. And the new thing that is happening in the last, let's say, 60, 70, or even perhaps 100 years is computers. And these computers are generating new paths that connect all these players. And I would like to discuss in particular these connections between physical laws and computers, between data and computers, and in particular humans and computers. And I would like to discuss if computing is or can be structured for the benefit of mankind. Now, computers and computing, you can say that the modern era starts with people like John von Neumann and Robert Oppenheimer, and perhaps with the Manhattan Project. And the Manhattan Project is infamous for this.
There it goes. The fourth atomic bomb has been successfully detonated.
So computers or computing can trace its beginning back to the Manhattan Project. And as you can see, people have been dealing with computers, or they have been concerned with computers early on.
Good evening. I'm David Wayne, and as all of you are, I'm concerned with the world in which we're going to live tomorrow. A world in which a new machine, the digital computer, may be of even greater importance than the atomic bomb.
So indeed, computers have been part of my life. I have a longer relationship with them than I have with my wife, for example, starting back in 1981. And you can see that this picture goes all the way to 1997. And I stopped in 1997 because after that, I was not programming or doing things. I became a professor. And then I had students of mine that actually began programming and doing great things in some of the biggest supercomputers of the world. What is important to see over these 36 years is that going from 1981 to 2017, the speed of computers has increased by a factor of about 20 million. So you can take any technology. Imagine you take a car, and a car that runs with 60 miles an hour after, in a span of about 36 years, is able to run 20 million times that. So this is a tremendous technology, and I would like to show you some of the achievements that we have been doing with it today. So the people in general, they started becoming aware of computers when computers actually started beating people in what would be one of the signs of human intelligence, in this being chess. And then people became very much aware of the power of computers when the Deep Blue beat Kasparov. But perhaps very few people are aware that Deep Blue beat Kasparov because of a bug. In fact, at some point, what happened is that it picked actually the best move, which is a medium-term best move. But then because of the bug in the algorithm, it didn't pick this medium-term move, and it picked another move, which was actually random. And then when Kasparov saw that, he said that this thing is impossible. Only a human could be doing such a thing, like sacrificing a short-term advantage for something that is happening later. Now, today, computers have improved. We can beat actually humans in other things that are even more sophisticated, like the computer game of Go. And more recently, couple of months ago, even beating humans on poker. And it's not that they are good at games. They're also good at replacing testing for atomic bombs. And what we can do today, we can actually do simulations that are replacing experiments and testing of atomic bombs precisely because we have developed such computing capabilities. Now, another game-changing technology that we are facing today is data. So today, there's about 5 billion devices, or about 1 billion people who have access to these devices. So it's important to distinguish that these devices are producing data. They're not necessarily computing, but there's nothing to escape all these kinds of data that are coming together. And I would like to argue that computers, humans, computing, and data are converging today And it's a wonderful opportunity that is presented to us. So a little bit about what we do with computers, or what do I call computing. So what is computing? It's about information processing, and it's about what can be computed and how to compute it. It's not only about computers, but it's also about posing the right question, about creating mathematical models, about making algorithms, creating software, being aware of a particular computer architecture, performing a simulation, analyzing the data, and eventually trying to reach a decision. And in the end, of course, you never stop there, but you keep looping and looping and looping until you go back and you change your question and you try to get to a better decision. To give you an idea, let me give you an example from ecology. So this is foxes and rabbits, and foxes are chasing, of course, rabbits. And there is some bizarre biology that I'm going to be telling you about, just to make the thing simpler. We're going to have rabbits. They're going to be eating grass and immediately giving birth, and they're going to be dying when they are eaten by foxes. We're going to have foxes that eat rabbits and they give birth, but they also die, perhaps out of old age. And I will introduce grass. Grass grows by rain. It dies by rabbits, and it can also die because of pollution. So this is something that maybe someone is interested to understand, what happens when you don't have just a fox and a rabbit, but when you have many of them. So you write down an equation, and you write down an equation that tells you how the population of rabbits is changing with time. This is this dr dt. And then it tells you how the number of foxes is changing with time. And then you write an equation that tells you how grass is changing with time. Now, this is great. What do you do with that? Well, you take the equations, you do numerical algorithms, and you create software. And today we are blessed to have amazing capabilities of just writing one line that is able to integrate all these equations without even needing to develop numerical algorithms, study stability, etc. And then after you do that, then you perform a simulation. So here's a parameter that I want you to pay attention. This is a parameter that says that if grass is dying due to pollution, it depends on this parameter epsilon. So if we set this parameter epsilon to 0, it means that the grass is not dying because of pollution. So we pick some other parameters for rabbits and foxes, and this thing is performing, and you see how the numbers are changing over time. You see this predator-prey architecture. Now, if you change it and you say, well, let's have some of the grass die because of pollution, then the dynamics are changing. And you see that indeed in the beginning you have that the rabbits are growing, and then the foxes are chasing them and they're growing, but then there's less rabbits, and then there is less foxes. But it's interesting to observe that as the grass eventually is going to be starting to die, you're going to see that there is less and less foxes, first of all, and then less and less rabbits that will be happening. So this is some of the things that we do in computing. Of course, today we don't do it only for 3 differential equations, but we can do it for trillions of differential equations, as I will show you in a second. So why do we compute? What does it give us? Well, it can complement theory and experiments, and there's a lot of things that we can do with theory that we cannot do with computing, and there's a lot of things that we can do with experiments that we cannot do with theory or computing, but I think the 3 together is a very potent combination. We can test hypotheses. There is a lot of activity happening today about geoengineering, and there's a lot of crazy things being proposed about how we can interact with the environment. Perhaps we can test such things in the computer first. We also have data. We can process and we can analyze data. We can optimize and design, and we can also, as I said earlier, decide. So it's omnipresent, and it's omnipresent in every field of science. So in the end, in my opinion, what do we do with computing is about acquiring and creating knowledge, and it's about trying to predict. And I would like to elaborate a little bit more on this topic. So what is knowledge? Knowledge, perhaps you can start to classify it in different ways. One of the segments of knowledge is how do you do something, and what do you know about something. And you can say that this how can be classified as classical knowledge, and the what can be classified as empirical knowledge. And if we go back to the Greeks, we can call that the episteme and the techni. And the techni is what became later artificiare, it became art. And then episteme usually leads to principles and laws, where techne usually is involved with heuristics and structures. And in the end, heuristics and development of structures, this is the job of engineers, and the development of principles and laws has been traditionally the job of scientists. What has been happening, in my opinion, in knowledge is that there have been silos that have been created, and often the two things, they will not be talking to each other. And where I consider that computing is enabling is that it gives us a common language, and it gives us a fantastic bridge to go between these two different types of knowledge, and I would like to demonstrate that. So let's look at classical knowledge. Here's Leonardo da Vinci, Old Man and Vortices. You're looking at the flow. You're looking at the flow around a plate here, and you can think about that. But then there came Newton, and he put down these equations of how the flow is happening. These are the famous Navier-Stokes equations I'll be showing you again and again. And what is the classical thing? The classical thing with equations and principles is that you can make precise predictions and you can provide explanations. At the same time, you can do that by few, rather expensive in terms of many terms, data and observations. And at the same time, what you have developed may not be useful for applications. And what is happening today is that these capabilities are greatly enhanced by computing. An example, very often maybe you look up in the sky and you see these contrails. This is the condensation of air that gives you actually markers of vorticity. Vorticity is what makes airplanes fly, and this is experiments that can be done, and people are looking at how these vortices behind aircraft are being destroyed. So you can do experiments, and this is more or less the knowledge that we acquire from experiments, but if you perform a simulation, then it is possible to get inside these contrails and look at the muscles of the flow, look at what creates the vorticity, look at what creates all these instabilities, and have very precise and very detailed information about instabilities and about how you can interfere with the flow in order to be able to learn about it and eventually to control and to manipulate it. So yes, we can do all these things, but there is a lot of things that we are challenged with. And one of the challenges that we have, I told you that computers are 20 million faster. This does not mean that the way we compute is 20 million faster. On the contrary, there is a big challenge in computing and the people who are dealing with computing that the software is not catching up with hardware. In fact, one can say that this is one of the biggest gaps of computing, and we are failing Moore's law in practice, and about 90% of the software is using less than 10% of the hardware, and this is an optimistic view. Now, what does this mean? This means that this is a problem that you have in energy, given how many computers you have, and how much does it cost to create a computer. So we make these expensive machines, but then we are underusing them. And another thing that is actually data tell us is that, for example, CO2 emissions in Germany are higher because of information and communication technologies, cooling of supercomputing centers, than the pollution that is generated by air traffic. So one of the challenges of computing is how to actually create mathematics and software that can actually use the computers in the most effective way. So we tried to do that, and the way we did that is by trying to solve an actual problem. We decided to write perhaps the fastest or the best code that ever was done in computational fluid dynamics, and to try, instead of using 10%, to see how high we can get on that. The problem we decided to study is something that is called cloud cavitation collapse. The idea is that when you get to boil water, by increasing the temperature of the water, you get bubbles. There is one more way to get bubbles, and that is by decreasing the pressure of the water. You decrease the pressure of the water when the water is going very fast. So that's how the bubbles are generated over the airfoil. And when these bubbles collapse together, they generate huge pressures. And these huge pressures, these little bubbles, they can destroy propellers. And at the same time, people are using them in order to destroy tissue that exists between blood vessels and tumors, and actually use them in order to destroy this tissue so that when drugs are coming out of the blood vessels, they can actually arrive onto the tumor. So they're doing that by putting here, they have injected bubbles together with the drugs, and then by doing ultrasound, they're cavitating. Their bubbles are collapsing, destroying the tissue the same way that are destroying propellers. Now, what people have done in the past is that you understand that by the destruction power of this process, it's very difficult to do experiments. And by the complexity of this process, it's very difficult to do theory. In fact, the only theory that exists is what happens to one bubble. Now, what we do is we take the equations, and I can tell you these are continuous equations. You have to discretize them. You put them into the computer, and I'll tell you in how many points we discretize them in a second. I want to show you the complexity of this, and this is one of the largest simulations, actually is the largest simulation ever made in computational fluid dynamics. This is the problem of cloud cavitation collapse. You see a part of these bubbles. You see the yellow, which is the pressure that is happening at the center. The movie that you see lasts a few seconds. In practice, it lasts less than a microsecond, this whole process. So that's what computers can do. They can go down to less than a microsecond and less than millimeters and be able to give you these processes. So we do the simulations, but we do them in order to understand, and we understand that nobody, in a way that nobody ever seen before, and actually I'm happy to show you this for the first time. We actually find that when the bubbles are collapsing, what happens is that there is fluid that is coming inside the bubbles. It is being accelerated by the stretching of the bubbles, and so we know now that cavitation collapse can be derived as interactions of microjets. So I told you that we set out to do the fastest code ever, and this is the fastest code ever in computational fluid dynamics, and it goes to say about the international collaborations that coming from Switzerland. We were able to get access to the Lawrence Berkeley and Lawrence Livermore, in this particular case, National Lab. They gave us access to 1.6 million cores. We were able to run our simulations there. And what has been an amazing achievement for us, there is something called the America's Cup, as you know, for yacht racing. There is the Gordon Bell Award that is also being something that is done in computers. So we were fortunate, again, thanks to collaboration with our colleagues between Switzerland and the US, to be able to demonstrate of doing simulations using trillions of computational points. Today, we can reach 100,000 bubbles, and we can actually compress data by a factor of 100, which is also an important achievement. Just to give you an idea of what has happened when we ran our code, we took our code, actually, and we ran it on the machines in Germany. And the machines in Germany, they will tell us, we cannot run your code. And then we will tell them, why can you not run our code? And then this is what they told us. You know, when you start to run, instead of 10%, at 70% of the machine started to shake, and they had to physically go and screw down the cooling units so that they could run our code. So this is actually counts much more than the previous numbers that you have seen. But all these things have been resolved, but this is actually real engineering in order to be able to run a code. I want to show you one more landmark simulations that was done thanks to my students. This is another problem that I will tell you in a second. This is a microfluidic device. This is a copy in the computer of microfluidic device that is being designed by Mehmet Toner here at the Harvard, at the MGH. And what is the problem? We're looking into cancer, and 90% of cancer is attributed to metastasis. When tumors are growing, they are emitting growth factors. These growth factors are actually cheating the blood vessels to grow. And when the blood vessels are growing, they arrive to the tumor, and the tumor finds a way to escape through the blood vessels. So we want to find out if the blood is containing tumors. So the processing that people have to do is you have to find one circulating tumor cell in 1 billion red blood cells. So there is an ingenious device that was developed by the group of Mehmet Toner, where by taking advantage of some fluid dynamics processes, they are able, through empirical ways, actually, to distinguish cells by size by taking them to go in different parts of the domain. And what we have achieved, actually, is to be able to go down and to simulate every red blood cells up to 0.2 milliliters of blood In this particular case, you are visualizing 200,000 red blood cells in the same microfluidic device. It's a millimeter-long microfluidic device to appreciate the size of the domain. So we can repeat the same experiment that the group of Mehmet does, and we can actually try to do optimization of the different panels and of the different geometries that you see here. So we put down the red blood cells, and then, as you will see in a second, we create a model of a circulating tumor cell. And what we do is we take it and we implant it there. And then we try to see if by continuously flowing this thing, we are able to separate red blood cells from tumor cells. This is a homage to the Fantastic Voyage, for those of you that are old enough to have seen this movie. It's quite a lot of effort to be able to do that. But to cut a long story short, you start the particles there at time 0, and indeed, after about the same time that it will take in an experimental facility, of course it takes much longer to compute, we are able to separate tumor cells from red blood cells. So this is the classical way, I call it, of knowledge, where we're setting up physical laws and we're using the computer in order to advance it. My original training has been on empirical knowledge. It has been about using dependencies from data or using experience. And ship design, there has not been a lot of science in designing ships. There has not been a lot of science in designing the first airplanes. You are imitating what other shipbuilders have done. You're using heuristic rules left and right, but somehow there's a lot of the things that are flying today and swimming that are based on this approach. So the empirical way is about statistical predictions at best. It's not about the precision that physical laws have. So it is expensive because it requires that you have a lot of data and a lot of observations in order to do statistics. And it relies that these data and observations have to come in a certain way inexpensively. And of course, this inexpensively is changing today from computers. And the last thing is that empirical knowledge has a practical utility, but has a practical utility for a given application. When you do a training as a naval architect, you cannot go and become a cell biologist. You cannot go and even become an aeronautics engineer. And so this empirical knowledge is very useful, but it's very limited. But at the same time, this is changing today because of computing. And if you decide to focus on computational aspects of empirical knowledge, you're returning back to similar problems that you encounter in classical knowledge. And for me, this has been the pathway to go from naval architecture to cell biology by finding common computational problems. So I would like to show you, well, these are examples actually of empirical knowledge. This is about machine learning algorithm, which I call empirical knowledge, and I will argue later, of looking at images, being better than humans, looking at text, being better than lawyers, and using the power of computers in order to derive things. Of course, when you have a code that does that, it's not the same code that does that in terms of machinery, but both of them, they share the aspect of being empirical in the way they proceed. We also follow that, and I was very happy to meet here, actually, Manuel Dominguez Rodrigo. Manuel is the husband of Mary Pendergrass, who is also a fellow, and we work together. And over a lunch, he asked, can we use some of the machine learning things you do in order to distinguish marks made by weapons versus marks made by trampling over bones? So we did that. It has been a wonderful collaboration. And we're basically trying to answer when did the humans start to hunt? So by distinguishing what is a cat mark and what is a trampling mark through machine learning, we're trying to answer. I think this is a very important question. But let me give you a more elaborate example of how you can use data and to give you a warning as to what machine learning can do by looking at trajectories. So here is trajectories of viruses, and we have done classification using support vector machines, where by looking at characteristics of the particular trajectories, we can distinguish what is the thing that the virus is doing. And we are very much interested in places that are marked in red, because these are the times that viruses are going on straight segments. Now, the knowledge about viruses and how do they move around inside the cell is very limited. We know that they attach themselves to microtubules, but microscopy is not good enough to tell us how many attachments they have. And then we resort to movies. This is done by a company called BioVisions here at Harvard. These are microtubules, they're inside the cell. And then we get here a vesicle, and then there are proteins that are moving on these microtubules. The viruses are recruiting them, and these proteins are bringing them either to the center or to the outside of the cell. I was interacting on that with a guy called Ari Helenius at ETH, and we actually wanted to examine different hypotheses by looking at trajectory data, looking whether kinesin and denane, the blue and the green, are together, whether you have only one of the two, or there is another secret molecule that is acting. The way we did that is we took the trajectories, we analyzed them, and we looked at straight trajectories because that's when we thought that the viruses exists on the surface of microtubules and is doing a directed motion. And we specified a model. It's a stochastic model. It contains 6 equations here. And the 6 equations tell you, for example, that you have denane attached and denane moves. You have kinane attached and kinesin moves. They move in opposite directions. You have that they unbind, and you have them that they bind. And now the whole thing here is, yes, you write this model, but you say, I do not know what are the rates under which these equations are operating. So you have to do some reverse engineering and use the data in order to find these rates, because you cannot really do first principles. So we do that, and we specify probability distributions of the velocities that we get from the data and the distances that the viruses are doing. We're doing some expensive optimizations in the sense that it takes millions of function evaluations to do such optimizations. And the net result is that we are able to find out what are all these rates, or when the experiments and the simulations are agreeing in terms of their probability distributions, we know what are these different rates. And then we can specify that it has been a stochastic tug of war. But we can do even more besides these things. We can actually find out, by playing a little bit with our model, where these proteins are attaching themselves. So by optimizing our model further, we find that we can predict better the data when the binding sites are 10 and 15. Now, when the viruses are inside the cytosol, there's 3 proteins where that are existing on their capsid, and these 3 proteins are the places where a kinesin and denane can attach itself. So now if you take a microtubule and you project it over one of the sides over here, then you find out that the amount of places that you can attach yourself are between 10 and 15 indeed, and this has to do with these hexon-hexon interfaces, not with this P9. So we did that, and then the biologists in our group, they destroyed P9, and then after that, we put again the viruses, and the viruses were able to move inside the cell. So this is a prediction by a computer model as to what part of the virus you destroy. And what we find is we published this paper, and actually a week later, another paper came out from a completely experimental group that they actually have reached the same conclusion by doing experiments and playing with the different factors. They identified that viral capsids, it's actually, the hexon subunits is the place where kinesin and denane are attaching themselves and are moving the viruses. So you can imagine that when Google or other places have access to your trajectories, they can process trajectories, and a lot of information can be inferred. I would not be surprised if people know what I have inside my refrigerator by looking at what is my particular trajectory. Now, I will come back to that. So this inference is actually, again, this is a very powerful process, and you can take data from trajectories and look at structure. So this is, again, a comparison of the 2 knowledges. And as I mentioned earlier, I consider that now computing is coming together and is putting it together. We can actually use first principles and do statistical type of calculations because we can afford to do many of these things. We can actually take this possibility that the principles are not useful and combine them with data and actually create new practical utilities for given applications. But there's 2 more things that we can do that we could not do before, I think, and this is thanks to computers. One is to, for the first time, understand that Newton and all these people that they put forward the equations, there is a problem. And the problem is that there are imperfections in the ways people derive equations, and there are uncertainties. This is the first thing that I would like to tell you. And the second thing is that heuristics, the same way that first principles can give you guidance for causation, heuristics, when combined with first principles, can actually lead to causation. And again, both of them are thanks to the capabilities of computers. So what is about imperfections and uncertainty? So I gave you a model that I made earlier, but the model was about foxes and rabbits. And then at some point, I created a mathematical model about the foxes and the rabbits. Then I made a computational model. I could have compared with experiments, as I have done in my other simulations. But everywhere when experiments and mathematical models are being compared, when computational and mathematical models are being compared, everywhere there are errors. There are errors in modeling. Maybe there are terms I forgot. There are errors in experiments and errors in my models. There is discretization errors. You write down an equation, but you corrupt it when you put it inside the computer. So out of all these imperfections, you have to acknowledge imperfections if you are to be able to arrive to knowledge and to be able to quantify imperfections and uncertainties in your predictions. So this process of uncertainty quantification on mathematical models has been very important, and here is an example.
Tom Menino is defending his decision not to close the schools there today despite a snowstorm. He says he got conflicting forecasts. And when severe weather is approaching, when you hear us talk about the European models, we don't mean anyone who wears fancy clothes walking down a runway. Those multicolored spaghetti lines on the weather maps when big storms are approaching, those are all computer models, predictions. Some are from our government forecasters, but increasingly, the European computer...
So this is the big success story of the European computer models was on the Sandy storm, where
the question is, Tom, do we need the push broom or the great big shovel out here? We really don't need either.
And the Weather Channel's Jim Cantori.
So, and what does this? What are all this? What this thing says basically is that that depending on the model you get, you have parameters. You may get a different forecast from one model. You may get a different forecast from the other model. And I should tell you that the European medium weather forecast model also fails in other cases. So whenever you hear an answer from a computation, the same way that in the past we would go to experimentalists and ask them for error bars, you should go now to modelers and ask them also, like people like myself, and ask us also for error bars. So these error bars are becoming important. For another, I'll give you another example about that. You look at experiments, people study how much water is flowing in carbon nanotubes. The dimensions you see across there is 2 nanometers. And then people are studying how fast you can push water, and you can push it orders of magnitude faster than if this was a much larger pipe due to peculiarities of the molecular level. But what I want you to observe is that these are order of magnitudes, and you can see even for the same length that you have 2 or 3 orders of magnitude differences on the results from experiments. Or one experimentalist will run this experiment and will get a factor of 1,000 different than the other. Both of them will publish their papers, but the question is, why does it happen? And the same error bars actually appear in simulations. So in simulations, we do molecular simulations. We have parameters because of the models we use, the parameters we choose, the way we do the computing, and then we use measurements to calibrate. So depending how we calibrate, we can get also different models, and depending what kind of computing resources we can run, for example, a weather model at the size of 1 kilometer resolution or 100 kilometers resolution, and that makes a big difference. So we go back to a theory that came back about the 1700s, and this is by Bayes. And the idea is that you have to use theories, but the theories have to be charged in terms of probabilities in light of the evidence. This is Bayes' formula, and if you replace A here, what is the probability of a certain hypothesis given the data? You have to do that by looking at this thing over here, which is the likelihood or the evidence. What prior information do you have? And then you create a posterior. So once you calibrate it and you have this probability distribution, then you can go and predict something, but you predict only with probabilities. So instead of giving you a value for epsilon that I gave earlier to be 0 or 0.2, now I would give a probability distribution because this probability distribution came from data. So when I predict how fast water is going inside the carbon nanotubes, I give again a probability distribution about my results. Now, where are the computers in there? Well, the computers are in there because to do these probability distributions, you have to do high-dimensional integrals. For every parameter, you account for an integral for one dimension. This is a highly dimensional problem. Without computers, the theory of Bayes has been there for 400 years. It's only now that we are able to access it, and we are able to do wonderful things, in my opinion, with it. Last one, heuristics and causality. This is about an algorithm that you all know, and this is the algorithm by Charles Darwin. It's about evolution, and we use this algorithm in order to do design. Instead of having genes, we consider parameters of an engineering system, and then by evolving this engineering system in a probabilistic fashion, the parameters in a probabilistic fashion, we're able to do reverse engineering in the most powerful way. In mathematical terms, you can put evolution in that sense. I will not go into the details today, at least, but I want to show you some examples of what is it that we do. You can use that actually to compute behavior by reverse engineering, again, data. So one of the data that we look at, this is a little fish, and is being chased by a big fish. And the little fish is escaping constantly. So people have been fascinated by the way the little fish are escaping in the water. So actually, if you want to see it a little bit up, more close and personal, is what these guys do is they sense the water when the mouth of the predator is coming, and then they're able to escape. But the way they escape is very, very peculiar, and it's encoded in their nervous system. What they do is when they're disturbed, they're doing something that is called a C-start. And a C-start is this bending of the body so that it looks like a C. And then you can see how fast it is that the camera is actually losing it from the frames here. People have done experiments, but you can do an experiment. You can visualize the flow. You still don't know if this is optimal. But if you formulate it in the computer as an optimization problem, you can find out if nature is optimal. So what you do is you specify, you take the animal, and you take the geometry, and you specify some parameters. You specify a cost function, and then you give it degrees of freedom to discover different motions. So you do that, and you start with a motion that is fish-like. And in this particular medium, or flow viscosity, if you like, it doesn't go very far. But it goes very far when it's doing the C-start. So the C-start actually was an outcome of the optimization. After 8,000 direct numerical simulations, we were able to discover that. And we're able to compare with experiments. We find the center line is the same deformation in the simulation and in the experiment. But all this thing is no explanation. The explanation comes through a very nice idea of Wim van Ries, who is in the audience. So we look at this thing. This is the vorticity. This is great. But what Wim and Mattia Gaggiola did is they looked at what this body of the fish is doing. This is a little animal, so in order to push fluid, it has to use all its body. So what it does is it engulfs as much fluid as possible, and then with a swing of the tail, is getting out of there. So using heuristics, using these evolution strategies, and using direct numerical simulations, we have looked into optimality in nature. And the last question that we asked in science, if you like, is about fish schooling. So fish schooling is one of these magnificent patterns that you see in nature. And you ask the question, do these guys have a choice that they school, or is it their fate that they are doing that? So we're trying to understand that. And we start by doing it in a more humble way. We start with two fish. So this is filmed with an iPhone. So you look at these two fish, and you look again at what they do, and you try to understand what is it that they are doing. But before you do that, you have to find out if this is efficient to swim behind someone, or what is it that you gain. But to do that, you have to put two fish to swim together. And to put two fish to swim together, it's very difficult, first of all, because no simulation capabilities existed to have two self-propelled bodies, but we have resolved that. But what you see here is you put two fish, one behind the other, and you give them an initial motion, but then the second fish is actually speeding up and is catching up with the first guy. So you say, aha, that's what happens. But then you move the second fish a little bit behind, and this optimization does not work. We threw every optimization technique we had. This is not an optimization problem. This is something else. This is a reinforcement learning problem. A reinforcement learning problem is Pavlov's dog problem. The idea is that you have an agent, and an agent is experiencing the environment, is acquiring information, and the key thing is reward. And once you have the reward, then you are able to find the optimal policy by which you're moving. Now, Guido Novati is in the audience, has done a lot of work about that. But just to give you an idea about reinforcement learning, I use this example usually. It's about bugs solving problems. So here is a bug, and he has a problem. And the problem that he has is what you see right here. So he has to solve it. So he tries very hard. This is a 3-minute movie from the movie Microcosmos. You're not going to see all 3 minutes of it. It has been edited. So you see, he tries. It doesn't really work. And then what he's going to do in a second, he's going to be almost solving the problem, but not quite. Then he gets the idea of trying another way. He goes around, but then he is going to totally miss the point. But to cut a long story short, this guy is actually successful after real time of 3.5 minutes, and he's able to, you feel like applauding after seeing these 3 minutes. So this is reinforcement learning without the math. So what we do is we take actually fish and simulations, and we have actions, which is how we move. We put states, which is to see the other fish, and we put a reward to find out if you are efficient. And what we find, it's actually the second fish has the option to not swim behind the first fish, but because of reinforcement learning, he finds out that there he can actually go and harness the wake of the first animal and increase its efficiency. This is more spectacular when you see it in 3 dimensions. This is one-of-a-kind simulation again. In my opinion, it ranks up there with the cavitation and the red blood cells, because it's the first time that someone sees 2 self-propelled swimmers that together actually have learned to follow each other. And this is an early learning, and this is a later learning that you will see that the second guy, totally in an automated fashion, has learned to avoid the vortices that will disturb it from the first guy and goes in between. So through Navier-Stokes equations, and for the first time, Navier-Stokes equations and deep reinforcement learning, we do that. And actually what we are very much interested is to revisit some experimental results that people argue that fish stay behind stones and they are exploiting vortices to reduce their muscle activity. So we're moving into things like Cyberfish. This is how I fall asleep, by reading books to my kids. This is from a great book called Flotsam, but I thought it was magnificent because these are some of the ideas that we would like to do, combining the cyber and the real. So the cyber and the real has a long history. So this is now, we're going about computers, humans, and data. And there are things that talk about machina sapiens and how the humans and the computers and the data are coming together. So here's really David Wayne.
Even the scientists argue that one.
I don't believe that we can say yet that machines do think. I have a basic question which I always ask, and that is, are these producing anything really new? Until I see a machine producing genuinely new things, I will not agree that machines think.
I confidently expect that within a matter of 10 or 15 years, something will emerge from the laboratories which is not too far from the robot of science fiction fame.
This is Claude Shannon of Shannon Information Theory, and this is, again, a movie from the MIT archives that I found from the 1960s, and this is perhaps how humans think. This is The Vexation of the Thinker, one of my favorite paintings by Giorgio de Chirico. And talking about people and that have looked into machines, a lot of the things happened back in the 80s, and if you are very fast and you read all this, you will find people like Stephen Wolfram in there, and you will look that all this cellular automata was one of the early ideas of putting machines together. You will find actually down here the connection machine that I had the honor to compute. And you will find also one more person, which is Gerard Wichniak, which is the husband of Judy, that actually happened to be one of the pioneers working in this interface between machines and intelligence. And actually, at that time, people were thinking how to combine the two in order to create computers. Moving forward, today this interface of machines and humans is taking another dimension. We're talking about society, but we're actually coming to the level of talking about the digital society. And now machine learning can also be used for the digital society.
How is machine learning and artificial intelligence making Facebook different for people? How has it changed Facebook, the platform?
Yeah, I think AI and machine learning is really a key tool to help people manage just the tremendous amount of information you see every day. Every single time you log into Facebook, there are hundreds or possibly thousands of things your friends have shared that we could show you. And our job is to try to find absolute things that are the best and most interesting to you, the things you want to see and show.
So information is growing. And this is a picture of me trying to catch an Uber. And of course, this is the picture that I get from Uber. And you know the recent stories about what pictures Uber might be presenting you. So my information, which is actually, I consider it to be my product and to be considered, I consider also to be my property, is being shared. At the same time, I don't receive the same information from Uber. For example, I don't know how many people are waiting, so perhaps I can hitch a ride with someone else. So this story of the information is that this asymmetry of information that we produce and information that people have access is becoming more and more asymmetrical, and this leads to inequality. And I would like to use here a quote by Larry Lessig, who is a professor of law at Harvard, talking about a culture without property, or in which creators can't get paid, is anarchy, not freedom. And I would let people to make their own comments. But there is a lot of agitation that is happening today because of all these technologies, all this machine learning that I told you it's a wonderful tool to do discovery. At the same time, this possibility of accessing human data reaches the level of actually questioning whether democracy will survive big data and artificial intelligence. There are other voices who are actually questioning what is the effect of computing in people. So there is this professor from the University of Michigan, Kentaro Toyama, who actually showed this is the US poverty rate, and he looks at digital technology. And then you would have expected that when the internet appeared, the poverty would stay and stay down, or when Google appeared, something will happen to poverty. But poverty doesn't change, and it's indifferent to all these developments on digital technology. You would think that this would be a change in the charitable giving in the United States. Digital technology does not change that either. At the same time, what digital technology is doing is increasing the productivity of people, but at the same time, the compensation of people is not increasing proportional to their productivity. To put it on the other side, at the same time, we go back, and thanks to apps and thanks to Facebook and thanks to all these technologies, people in very remote areas, this is an example from people from ETH, that they're actually going and through a phone, they actually can examine children in remote areas in South America. You can actually use the Google Street View images in order to identify information about poverty, and perhaps one can do something about that. So all I'm saying is that we live in times that perhaps at some point we have to choose in which way we want to push this technology. So I argue that this is a critical time. And at the same time, something that I have experienced the last time that I've been here, you start to realize that also the mind, the human mind, needs assistance. We believe in untruths. We cannot distinguish things. We need some assistance in order to face this onslaught of information. So we have to put computers in good use. And I told you about Moore's law. Here's where Moore's law is going, and here's the brain is going. So when you are able to harness all this spectrum, I think there is great potential. Another way that I see it is computing as thinking, and there is this great book by Daniel Kahneman about fast and slow, and I consider, I consider the classical to be the slow, and I consider the empirical to be the fast way of thinking. And I think it's possible to combine the two and to come up with ideas similar to the fast and slow questions that we have, provided you know when to use what between these two ways of approaching knowledge and when to combine the two together. Here is a suggestion that comes. Here is a suggestion about us scientists. It came from an interview or a visit of Eric Schmidt at Caltech. I get this magazine as an alumni from there. What he says is that forget about doing hypotheses as humans, get as much data as possible, and without too much of a theory, begin to analyze the data. And the idea is that will be some reinforcement learning in there, and it will say you have a particular hypothesis, and then the machine will look at the data, and then you will find that your hypothesis may not be true. If you want my personal opinion, I actually find this to be a great and a very interesting idea if it's used at the right and appropriate way, because in a sense, very often when I advise my students, I also do perhaps what a machine could be doing better than me. At the same time, computers and suggestions are dangerous, and thanks to Radcliffe again, I was exposed to Mark Lombardi, and after being exposed to Mark Lombardi, I was exposed by my fellows here to Guy Debord. And actually, I found this statement by Guy Debord that was done back in 1964, where he's talking about there is all aspects of technological development. He focuses on communications, and he says that isolation of individuals, as well as control of these individuals by means of suggestions, broadcast by all sorts of leaders. So we have to take suggestions, but we have to think about these suggestions, and we have to create the knowledge by which we process these particular suggestions. Which brings us to one or two before the last, about this idea of computers and about AI. AI, I consider it to be a core technology in many fields today. AI has tremendous power that goes beyond humans, and the same way computing complements theory and experiments, I think AI can complement the classical way that we are doing our thinking. But at the same time, we have to be able to create new ways of interfacing with machines and computers. We have to be able to ask the computer, why did you do that? When do you succeed? When do you fail? You should be able to ask the computer, can I trust you in what you gave me? Can you explain what you just produced? And there's a great effort, this slide adapted from David Gagnon from DARPA, there's a great effort that's happening now about explainable AI to understand, to trust, and to manage AI. In closing, I think I would like to offer a definition for computing. Computing is knowledge that helps discover, predict, and explain structure. It's something that helps you to join boundaries, to go from fish schooling to nanoparticles for cancer therapy. And actually, I think there is a musical way to understand this interdisciplinarity, and this is this. This is from a group called Lambarena, and it's a combination of music from Bach and from Africa. It's about listening to the violin of Bach. It's about listening to the drums of Africa and finding the way of putting the two together in perfect harmony in order to be able to create great music. This is where I think we have the opportunity to go today. So computing is knowledge. I would like to put these things up and say the most important thing is the last one. It's about education. We have to change a lot of things in education of how do we teach people about computers, how do we teach about software making, how do we teach about data handling. So it's a lot about education, 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 and I think we should take into account these different modes of thinking in the way we try to teach people of the future. And I'd like to tell you that I think with the powers that we have today, I think we've never been in a better position. Having something that is 20 millions faster than it was 36 years ago, if we put it to good use, I think we can address a lot of the problems that exist today, and I think a lot of people are using computers and computing to do just that. So I'd like to thank you, and I would like to thank also myself, all my students and postdocs that are listed up there. The ones that are underlined are actually had an association with Harvard. 3 of them are in this room. I'll be happy to take any questions. you.